In this class, we will discuss about assortativity or homophily, the notion that the probability of observing an edge between nodes can depend on their properties. So the idea is quite well known in social network and in society in general. For instance, by the saying that birds of a feather flock together, or in French, qui se ressemble s'assemble. Which means that people that are similar tend to behave in a similar manner and tend to belong to the same groups or to interact more. So this is something which is quite well known, and you can see it in the network which is displayed here, where it's a network extracted from high school in which nodes correspond to students and connections correspond to friendship between the students. And the colors correspond to ethnic groups that were collected by the people doing the study. And we observe clearly that there are some stronger connection between nodes with the same color, which means that, well, it's not random relatively to this property. So the fact that these students observe these groups, and it influences the probability to connect between them. More formally, we want to observe both nodes at the end of one edge and to see if the two nodes which are the end of an edge tend to be more similar or not than expected at random. So the property that we might look at are not limited to anything. So you can consider, for instance, age, gender, nationality, political beliefs, socio-economical status, obesity, whatever. So anything that you can represent as a property of your node is something that you can study. And it has been shown in many cases that social networks and network in general tend to have often this property of homophily for at least some variables. It's important to note immediately that it's not because there is more edges than expected between nodes with the same property that it's an explanation of what happened. So, for instance, it's possible that people who were similar were more likely to be connected in the beginning, or on the contrary, that people that are connected tend to influence each other, and thus they end up having the same property. So, of course, it's not possible for ethnic belonging or age, for instance, but it's possible for opinions, for instance. It's very well known that people tend to influence each other, and so if they are connected, they might influence each other and end up having the same opinion, even though it was not the case in the beginning. So unless we have access to the whole dynamic of the process, we cannot know if this homophily emerged from a link creation mechanism, or from on the contrary, from an influence phenomenon. So, as homophily exists, there is also the contrary, so disassortativity or heterophily, in which nodes having different properties might also be more likely to be connected. So again, there is a common saying that opposites attract, and this can also be true for some properties. So a typical example would be a network with a sentimental or sexual relationship like this one, in which we observe a higher tendency of blue nodes to be connected with pink nodes. So there are some connection between blue and blue, there are some connection between pink and pink, but it's more likely, we observe more likely connection between blue and pink nodes. Another example can be predator-prey ecological network, in which you will have predators that are more likely to feed on prey, but there are also some super predators that feed on predators, for instance. So both of these phenomenon can exist in social network and in other networks, homophily, heterophily. So it depends really on the properties we are looking at. And the question is how to evaluate, how to quantify how strong this effect is in some network. So it depends. The first thing we can look at is if the variables are categorical or scalar. So if they are attributes like gender, color, shape, ethnicity, whatever, in which you belong to a group or not. So your gender is either male or female or transgender maybe, or if it's more scalar attributes like age, weight, income, degree, and so on and so forth. So the first case we will look at is when we have categorical attributes. So finite number of attributes, like for instance for genre or for ethnicity. And in this case, what we do is we use this formula. And in this formula, we have to compute first the fraction of edges between nodes with the same attributes. So for instance, you count how many edges you have between women, how many edges you have between men, and so on and so forth. And you subtract the expected number, the expected fraction of edges between nodes of the same category. So you will subtract the expected number of edges between men, the expected number of edges between women, and so on and so forth. So this probably reminds you what we already described for the modularity, and in fact we will see later how they are related. But for now, yes, this idea is to subtract the actual observed number of edges between nodes having the same property, and to subtract the number of edges expected between nodes having the same property. And we divide this by 1 minus this same sum that we had here, so the expected number of edges between nodes with the same attributes. So we make this computation, and the way to interpret this is that if there is no assortative mixing, so if the edges are random respectively to these properties, then the score will be 0. The expected number of edges is equal to the actual number of edges. If the network is perfectly assortative, then you will have a value of 1, and if it's assortative, you will have a value above 0. So the more it's assortative, the highest the value until reaching 1. Just to give a concrete example, so this is a fictional example in which you have blood types. And you imagine that we look at connection between people according to their blood type. And values are expressed as a fraction of all edges. So if you sum all these, you get 1, because of course it's all the edges. And we see that 30% of all the edges are between people who are both of blood type A. So you have maybe no edge between people who are B and AB, but you have 0.2, so 20% of edges between people who are B, and so on and so forth. And the way to compute this is to make the sum of the values on the diagonal, right? So we are summing a fraction of edges between A and A, between AB and AB, between B, and between O and O. And we subtract the expected value. So the expected value is, of course, in this case, between A and A, for instance, I expect to have 0.5 times 0. Times, so 0.25. 25% of the edges should be between A and A. So already we can see that this value is actually higher than what is expected. And so when we make this sum of the actual fraction of edges on the diagonal minus the expected number of edges on the diagonal, and as we have seen before, we divide by 1 minus this value, the expected number of edges, then we get this computation and this final score, which is, as we can see, above 0. So in this case, we can say that yes, this network is assortative. And of course, to interpret this value, we maybe need to go deeper into the analysis to see if it's significant, maybe to compare with other properties on the same network or these kind of things that we have maybe already discussed. There is, as I said, there is a strong relation between assortativity and modularity. In fact, you can express the assortativity as Q, the modularity, divided by the maximal possible value of modularity on this network. So why? Because if you look at what we have on the bottom of this equation, we see that we have exactly as before, as above. Sorry, we subtract this, but here we subtract to 1, and here we subtract to the fraction of edges inside communities. So it means that if all the edges are indeed inside, so communities for modularity or inside or between nodes with the same property, if all the edges are inside these groups, then you will have a 1 here. So this corresponds to the maximal value that you can reach. And so you're dividing the modularity by the maximal value of modularity that you could reach if all the edges were inside the same group, inside the same community, inside node with the same property. So you could actually use assortativity to quantify the quality of communities, or use community or use modularity to assess the homophily also. Instead, if we have numeric attributes, what we will do is to compare the values at both ends of each edge. So to better understand it, we can think about a plot like this one, in which each dot corresponds to an edge, and the position of this edge depends on the value of nodes at both ends. So for instance, here we can consider a bipartite network in which nodes on one side of the edge are husband, and on the other side you have wife, but it's exactly the same idea if you have a normal network. You will just have the same value on both axes. And so each edge corresponds to actually the position, the values of the attributes at both ends of the edge. So for instance, this is an edge between someone who is 34 and someone who is about 19. And we have this way, this kind of plot. And when you have this kind of plot, you know that you can use a well-known score of correlation, which is the Pearson correlation coefficient. And that's exactly how we will compute the homophily for numeric attributes. We will compute this kind of plots and then compute the Pearson correlation coefficient, and that is our homophily score. So I won't go into details of explaining the Pearson correlation coefficient, but you can just go to Wikipedia or any class online to find the detail of this measure. So the interpretation is the same as before. If you have 0, it means that you have no homophily, and if you have a value of 1, you have a maximal homophily, a maximal assortativity, and if you have negative values, you have, on the contrary, heterophily. So these scores are quite well known in the literature, and they are often used to compute to see if there is some homophily according to an attribute on your network. But they have, of course, some limits, and there are currently researches on how to improve on that. A good example is taken from this paper, in which the author proposed some multi-scale assortativity, and they make a difference between a local assortativity and a global assortativity. So what we have seen until now will be the global assortativity, but they show that if it can be interesting in many cases to look what's happening at the local scale. So for instance, the examples show that all these 5 networks, they have the same assortativity coefficient. They have the same score of global homophily, while in fact they look very different. For instance, you can see that here you have some very clear groups with orange nodes being connected mostly to orange nodes in this part of the graph. Here you have blue nodes connected to blue nodes, and here it's more well mixed up. And on the contrary, on this graph, there are no clear groups, and everything seems to be a little bit mixed up with everything between blue and orange. And but they have the same global value, and so they introduce, for instance, a local value in which you can now be able to differentiate, and that's what you can see on those plots. You can see that there is some global assortativity, some local assortativity, some local disassortativity, while here everything is kind of in the middle. So you have to look more in depth like this to observe what's happening in the graph. And they have shown some example on real graphs in which this phenomenon exists. So some parts of the network are assortative and some other parts are disassortative. So as always, it's a little bit tricky to rely on a single measure to really understand what's happening in the network. Another way to analyze this kind of complex relationship is through what we will call more generally mixing patterns. So mixing patterns consists in analyzing how a property is connected to other properties. And so here you have an example taken from this paper in which we plot for each age the strength of the connections to other individuals with other ages. And we observe that we have high values on the diagonals. And this means that we clearly have some assortativity, some homophily. So people of a given age tend to be more related to people with the same age, similar age. But we also observe some strong values outside of the diagonal. And in this case, clearly we can learn from this plot that people of age around 30 seems to be very strongly connected to people of age 0, 1. And you see this line, and it's growing like this and kind of stop when people of age around 40 are connected to people of age around 18. And of course, this can be interpreted in this case as a parents and child relationship. Okay, so people tend to be strongly connected to people of their age, or if they are parents, they are connected to their child. So it's often, it can be really interesting to make this kind of plots to really understand how the attributes influence the probability of observing edges between individuals. This is another example I already shown in the first class, in which we observe on Facebook the probability to be connected with people of the same age. And again, we can observe each line correspond to people having a certain age. So for instance, the blue line corresponds to people of age 30. And if we observe their contact, we observe that they are mostly connected to people of age 30, so about the same age as them. And this probability decreases with the distance in age. Okay, so again, this shows that attributes can be very important and interesting to study in the relation between the properties of nodes and the probability of them being connected. But a single score, like the homophily score, often is not enough, and it's interesting to go deeper into the analysis to understand the patterns of connection in the network. A particular application of assortativity is to compute what is called the degree assortativity. So the idea of degree assortativity is that we will take as a property of nodes not something that we know a priori, like age or revenue or whatever, but something which is internal to the graph, which is the degree of nodes. apart from that, the way to compute it is exactly the same. So we compute the degrees of each node. We take this as a numerical attribute, and we compute the assortativity coefficient on the graph, and we obtain a result. And it has been observed that in many social networks, this value is not zero, but is often positive. And you have some example in this table. And you see here that for many social networks, the value is indeed positive, with some counter examples which are negative or close to zero. In technological network, in this case, you observe many negative values, and in biological networks, you also observe this negative value, meaning that there is a degree disassortativity, in fact. So the question we want to answer with this degree assortativity is often, are high degree nodes connected to high degree nodes and low degree nodes connected to low degree nodes? So is there some kind of ranking, some kind of hierarchy, let's say, of nodes in which the popular maybe people in social network will be more likely to be connected to other popular people, while a non-popular one will be connected to non-popular individuals? And that's what we want to study with this degree assortativity. So in fact, this problem is so well known that often people use the word assortativity alone to mean degree assortativity. So be careful with that in papers. When you encounter assortativity without any other information, often it means degree assortativity, because it was introduced in this paper as assortativity, but in fact it was degree assortativity. Again, if we want to study it in detail, we can look not only at a single value for the whole graph, but details by values of the degree. So to do that, the typical way to do is to compute what is called the average nearest neighbor degree. So we already introduced this notion before, but simply for each node, we take all its neighbors and we compute the average degree of the neighbors. So we have already introduced a notion of the friendship paradox, but here it's a different notion. What we first can show is that if there is no degree correlation in the graph, then the average degree of the neighbors should be defined in this way, and this is in fact a constant. So this means that the average degree of the neighbors is independent of the degree of the node if the graph has no assortativity, no degree assortativity. So we can also look at the function defined in this way. And if the function is positive, then it means that the network is assortative. And if the network is disassortative, then it's a negative function. So let's illustrate this with an example. We see in this case, which corresponds to an astrophysics co-authorship network. And we plot on the x-axis the degree of node, and on the y-axis the average degree of their neighbors. And we see that for instance, for nodes of degree 2, the average degree of their neighbors is around this value. And if the value is 100, then you have this value, and so on and so forth. And what you observe here is that this value, this function is positive. It's growing. It's going up. So this means that there is actually some assortativity. And we see that if the network was not assortative, then what you would expect would be something like this, an horizontal line, because the average degree should be independent of the degree of nodes. On the contrary, if you look at this other network or about yeast, you see that the function is going down, So what this means is that you have a disassortative relation. Another example coming from Facebook, again, I have already shown this picture in the beginning of the class, in the introduction of the class, but now we can interpret it. If you remember, this corresponds to the relation on Facebook between the degree of Facebook users and a relation to the neighbor's average degree. So exactly what we have just described. And again, what we see is a positive function, while we were expecting, in a random case, some horizontal value. So it means that on Facebook, yes, it seems that, well, popular people are more likely than average to be connected to famous people, and low degree people are more likely to be connected to lower degree people. Even though we still have the friendship paradox with, for instance, nodes having a degree of 200, having an average friends degree of more than 200, right? So this was the friendship paradox. So, same as before, we can also observe that nodes having a given degree, for instance here a degree of 50, are more likely to be connected to nodes having a similar degree. So again, it's the same idea as before. What we show here is that by going into details of the relationship between degrees, we can better understand what's going on in the graph than just by looking at a single value, which is the assortative coefficient for degrees. So in this case, we can clearly observe that people having a certain degree are likely to be connected with other people having the same degree, same number of friends in Facebook.